Hello everyone. Today we're going to discuss the Basel problem with single variable freshman calculus. So what is the Basel problem? The Basel problem is to find the value of the sum of reciprocals of squares of the positive integers. It's evident that this series converges by the p-test when p equals 2, but what is its value? That's a much harder question. This was first asked by Pietro Mingali, who was an Italian mathematician born in 1626 in Bologna, in what is now Italy. Mingali studied sequences and series, and did work on areas in the plane that influenced both Newton's and Leibniz's development of calculus a few decades later. Interestingly, he posed this question before calculus was systematically developed. Every solution to the Basel problem requires a significant amount of calculus-based math, so it's no surprise that he wasn't able to answer it himself. The question was open for several decades until the great mathematician Leonhard Euler supplied an answer in 1734. Euler was born in 1707 in Basel, in what is modern-day Switzerland. His solution was celebrated, and the problem was honored with the name of his birth city. Euler discovered and studied the Riemann zeta function, defined here. This function is named after Bernard Riemann, because while Euler discovered it and drew some interesting conclusions from it, Riemann blew the top off it. It's only being mentioned here because it gives a concise way of writing the sum, whose value we're looking for, as zeta of 2. As to the value of zeta 2, it's pi squared over 6, which is quite unexpected and amazing. Euler's original proof is fantastically inspired and simply executed, but with some gaps that he filled a few years later. Some other but still worthwhile arguments may have less theory behind them, our own included, but they don't have the same wow factor. In fact, a zillion years ago, I was eating a hamburger at Fuddruckers with a friend, and he wrote out Euler's proof on a napkin, and I recall that moment of amazement to this day. There are some good videos that talk about the ideas in his argument, and you should check them out. However, unlike the proof we'll be presenting today, the details of Euler's proof are not explainable with basic calculus. Here is some context for the upcoming proof. In calculus, Taylor series and geometric series are used to evaluate concrete sums, examples being the alternating harmonic series and Leibniz's formula for pi. Instead of these tools, we're going to use a cosine sum to evaluate zeta of 2. As an aside, Euler's formula shows that there is still a geometric series in disguise here. The cosine sum appears as the real part of this complex geometric series in equation 1. You can unpack this bit at your leisure, but we're not going to linger on it here. The upcoming proof is fully accessible with techniques that you learn about in single variable calculus, and there's nothing about complex numbers that you need to know. So what is the connection between cosine sums and zeta of 2? If we proceed informally and integrate the cosine sum twice, ignoring bounds and constants, take n to infinity, and evaluate at 0, then we have zeta of 2 popping out at the end. This observation is probably the easiest to stumble onto initially, and it shows an obvious connection, but the best way of pursuing it uses Fourier series, so that's not the approach for us. We're going to do something similar but easier with Lagrange's identity equation 2, which gives an explicit formula for the cosine sum. Since Lagrange's identity is the basis for our proof, we're going to derive it. Take the cosine sum and multiply and divide by sine of t over 2. This is allowed because we know that t over 2 isn't a multiple of pi. Now we can use the product of sum trig identity to write the sum on the right as a telescoping series where the only terms that remain are the first and last ones. Distributing 1 over sine of t over 2 and simplifying gives what we're looking for. The cosecant term in Lagrange's identity has an infinite discontinuity at 0, so we can multiply both sides by t to remove it. We can do this because of the small angle approximation and the fact that cosecant is the reciprocal of sine. Note the function h of t defined here is continuous on the closed interval from 0 to pi. So equation 2 can be written as follows with no discontinuities on that interval. Finally, integrate from 0 to pi, With the exception of a small argument at the end, the rest of this video will be addressing the two integrals in equation 4. Let's evaluate the integral on the left-hand side of equation 4. We're going to replace n by 2n and apply integration by parts, where u is t and dv is the cosine term. The reason why n is replaced by 2n will be clear soon. The first term in the sum evaluates to 0 when we plug in both pi and 0, so all we're left with is the integral of v du, which evaluates to cosine of kt divided by k squared. When we plug in pi and 0, we just get minus 1 to the k minus 1 in the numerator. Now the numerator is non-zero only when k is odd, so we replace k with 2j minus 1, where j ranges from 1 to n. The fact that we changed the top index from n to 2n simplifies the top bound for j in this last sum. By equations 4 and 5, we start seeing pi squared and a term that looks a lot like a chopped off zeta of 2, except that the denominators are all odd. However, this is a detail that will be dealt with at the end. The biggest remaining step is to get a handle on the integral in equation 6. Let's examine the integral by taking a look at the graph of h of t and the graph of h of t times the sinusoid when n equals 20, which is the one from the thumbnail. Multiplication by the sinusoid turns h of t into a function whose negative part is more or less a small shift of its positive part, so we expect the integral to be close to 0. More precisely, we suspect that the limit of the integral is 0 as n goes to infinity. See equation 7. This is indeed the case, and we'll verify this using integration by parts. The idea is that if dv is the sinusoid part, then both terms in the integration by parts formula will have a bounded numerator divided by 2n plus 1/2. It's worth noting that in general, multiplying an arbitrary function by an increasingly oscillating sinusoid doesn't make the limit of the integral 0. In the next slide, we'll use the fact that we got rid of the badly behaved infinite discontinuity in cosecant of t over 2 when we multiplied Lagrange's identity by t to get h of t. To apply integration by parts to the integral in equation 7, we need to know that h prime of t is continuous. This can be done in a brute force way using the definition of the derivative and limits and so on, but it's more instructive and intuitive if we use power series. The function g of t defined as follows is clearly continuous and non-zero on the closed interval from 0 to pi because of the small angle approximation, but the derivative is also continuous. Why is that? Because g of t is a power series with radius of convergence infinity that is equal to the power series of sine of t over 2 divided by t over 2, and power series are infinitely differentiable on their open interval of convergence. Now h of t is 1 over g of t, where g of t is non-zero on 0 to pi, so h prime of t is minus g prime of t divided by g of t squared, which is a ratio of continuous functions, and therefore h prime of t is continuous. With that technicality out of the way, we can proceed to the integration step, where u is h of t and dv is the sinusoid. The first term evaluates to 1 over 2n plus 1/2, since cosine of an odd multiple of pi over 2 is 0 and h of 0 is 1. This term is quite simple, so we just have to deal with the more complicated integral in equation 8. Now, since cosine is between minus 1 and 1, we can say the inside of the integral in equation 7 is at least negative the absolute value of h prime of t and no greater than the absolute value of h prime of t. If we integrate through this inequality and divide through by 2n plus 1/2, we obtain upper and lower bounds for the integral in equation 8. The upper and lower bounds have limit 0 as n approaches infinity, so by the squeeze theorem, the limit of the integral in the middle is 0. This is equation 9. By equations 8 and 9, we have the desired limit in equation 7. And finally, with equations 6 and 7, taking limits, we have the following formula, equation 10, for the sum of reciprocals of all odd squares. Now, what we're looking for is the sum of reciprocals of all the squares, not just the odd squares, but this is just a small step at this point. We've already gone 95% of the way. What we can do is write zeta of 2 as a limit of partial sums, where the top bound is 2n. Then break the partial sum into odd and even terms. The first partial sum is 1/4 of a partial sum of zeta of 2, and the second partial sum is one whose limit we just computed in equation 10. Taking the limit, we finally have a simple equation that zeta of 2 must satisfy. Solving this equation gives the answer pi squared over 6, and we are done with that. Putting this together was a lot of fun. I get a real kick out of making a challenging result as accessible as possible. Subscribe if you like what you see. Also, let me know what you think of the video in the comments, and if there's any content in particular you would like to see. Have a great day.